A little bit about our company. We've been building ultrasonic equipment to control algae and biofilm since 2016. We manufacture, engineer everything in East Tennessee in our own facility. We have our own engineers, our own clean room that builds the boards. All assembly and everything is done in-house. He started this program back in 2016 to help rid chemicals from the water. It's something Tony's very passionate about. He develops these things. We're constantly in trials. What we're going to talk about today, though, is we're going to talk about how you can control biofilms and algae in your wastewater, drinking water, and recreational lakes. We have great success in lagoon-style wastewater, natural reservoirs. We use those all over the world. It cuts down on the chemicals that they have to use, things like that. Let's see. Okay. So how does ultrasound work? Okay. On blue-green algae, it's going to burst the gas vesicle on the inside. It does not lyse the cell, so we're not releasing bacteria into the water. What it does is it disables its floating ability. So it cannot, when it germinates down here, and it starts floating to the surface to get sunlight for photosynthesis, we disable its flotation. So it sinks back to the bottom, no more light, no more algae, okay? So in other types of algae, we'll actually separate the cells on the inside from the cell walls. So it disables, it actually overconsumes, and it sinks to the bottom and dies off. It's naturally consumed. In wastewater, when we first put these in, sometimes you'll see the TSS rise up real fast in the very beginning, but then it drops off. It's just where it's breaking stuff up. It's actually separating the cells, things like that. Let's see. So as you can see here, it starts to separate. This one's after 3 weeks. So you can actually see the cells breaking down. Okay, and blue-green algae, this is what we were talking about. It actually separates the gas vesicles. It collapses them. It doesn't destroy the outer wall, so nothing is leached back into the water. So we're not lysing it. That's very important that we're not releasing that back into the waters. Okay, so here is under a microscope. This is showing the outer walls are being permeated by gas. You can actually see it start to collapse. The untreated cells, you can see how nice and round. Then we start to destroy that outer cell wall. As I was talking about, we're separating it from the cell wall so it can't control itself anymore. And it sinks to the bottom and dies off. Okay, here on the green algae, it's a little bit different. You can see this study was done back in the UK with our systems several years ago, but you can see after only 7 days of exposure, it's already starting to break it apart. You can see it start to tear it apart from the cell walls, and it's going to start consuming. It'll just die off. It can't communicate with itself. It's not feeding itself. It dies off. Okay, what is biofilm? Biofilm is in every body of water. It's just not a problem until it starts to colonize. And that's when you get that film surface built up on everything, the slimy stuff. What we do is we actually use, there's sound pressure. So the way these systems work is they're emitting ultrasounds, and it's mimicking sound pressure. So it's mimicking movement. So the biofilms do not want to colonize. They do not want to stay in one place. It's just like a biofilms on a rock in a river. They're always on the backside where it's calmer, and it always builds up there. So what you're doing there is with the mimicking of movement, and we can do this for about 3 acres. You won't get the slime buildup on the walls of the tanks. We use it in a lot of tanks. Use it clarifiers, things like that. So less downtime, less man hours put into scrubbing it. We can reduce down your time sometimes by half. So you don't have to get in there and swap tanks, pressure wash, shovel, get all that back out and then refill the tank. So save you man hours, save you labor, and a lot of time pressure washing. But it'll stop the sludge from accumulating. You'll see when biofilm starts to build up, it actually colonizes, and then they have parts of biofilm that just are there to hold it onto the wall, and parts of it that are feeding, and they actually become a community. So they actually have little holes in the biofilm that it intakes nutrients and it expels nutrients. So that sound pressure takes it and moves that around, so they don't want to colonize. They don't want to build up to that point. Okay, now we're going to talk about critical structural resonance frequencies. Okay, so everybody has seen how this works. You got the opera singer with the wine glass, things like that. Everything has a resonant frequency. The closer you can get to that, the better you are at destroying it. Even motors have it, buildings, everything has it. Our bodies have it. You can feel vibrations in your body that's getting close to your critical frequency. So the way we do this is we use several different frequencies. My company, we use about 2,500 frequencies and harmonics. So like with a wine glass, you dip your finger in there, you rub it around the rim. That is its critical resonant frequency at that particular moment. But there are things called damping. Damping is the environment around it, the amount of liquid in the glass, the thickness of the glass, the humidity in the air, whether that glass is on a cloth or on a hard table. It all is a factor in this. That's why we have to use so many different frequencies. If there was just one frequency for algae, I'd be more than happy to put it in there and just run it, but it's not. It's all dependent on distance, your TSS, the temperature of the water. All these things come into play when you're talking about a critical resonant frequency here. So there it goes. So when you hit that frequency, that's what happens. Same thing with algae. It happens with everything. So when you talk about the critical resonant frequency doing this, the dampening is a big factor. It's a very big factor. The amount of sludge you have in there, the amount of algae, the size of the algae, is it just germinating? Is it fully matured? Is it gone through several cycles? And when we hit that perfect frequency on it, or one of the harmonics of it hits, it goes ahead and destroys the algae or the biofilm and moves it, things like that. A lot of times in drinking water, we'll actually run a 2 transducer system, one towards the top and one towards the thermocline. And what we're doing is we're getting it as it starts to germinate there at the thermocline, like a large drinking water reservoir. We'd put it down low, and as it's starting to mix and get its nutrients, and algae germinates and it wants to start rising, we start to kill it off there. And then we also catch it towards the surface. We usually run about 18 inches below the surface with ultrasounds. And we catch it when it's trying to get sunlight, because it needs sunlight to grow. It goes up there, it digests its food, it sinks back down, gets more food, rises back to the surface. So we try to catch it in 2 places in drinking water reservoirs. Now in wastewater, in like lagoon styles, we usually do in a 3 lagoon system. We'll use it in 2 lagoons, because you usually have heavy aeration in the first one, then you have some aeration in the second, and then you'll have no aeration in the third. So we use it in the second and third, and they're very easy installation. You can have different types of power out there. So like out there at Olympia, we've got to use solar power. So we have a stand-up that just buries in the ground to about right there. You run the cords up, you plug into the back of the solar controller. It's got 6 batteries on it. You run you hook your transducer to your float. You hook a cable to it, you pull it out towards the middle, and you stake it off on the other side. So anytime you need to clean it, you just go pull the steel cable on the other end, pull it to the bank, wipe it off. So that's kind of important with ultrasounds, with all ultrasounds, is you have to keep the heads clean. You have to keep the transducers clean. Maybe once a month, pull them in, wipe them off. It's not much. In other areas, you can use AC power, or in remote locations, like in a lot of drinking water reservoirs, we use a float system, and it has everything built into it. It's kind of like the land-based solar. The batteries, everything are built into it. Transducer hangs below it. You can also hang 2 transducers, so you can get down to the thermocline, get it germination. or in a lot of cases, they'll use a sonde unit for water quality monitoring. And it actually will transmit back to the web page and show you what's going on with your water. And then you can actually see, you know, what adjustments you need to make. That's a pretty advanced system. But most everybody, AC and the land base, very easy to take care of. The AC power runs on anything from 84 to 265. So it doesn't have to be a special power supply for each type of setup. It's pretty universal. In wastewater, we can put them anywhere from like the second clarifier on. In any holding tanks, things like that, we can use it to cut down the biofilms on the wall. We can also, in the lagoons, cut down the algae. You know, first lagoon, you want the algae to start consuming, heavy aeration, things like that. Second and third, that's where we usually place our systems. Any one of those tanks, you can use them in. We do offer, a lot of ultrasounds they're either all ultrasound is line of sight, okay? It's like shining a flashlight. If there's a barrier there, it can't go through it. It'll go around it. There will be a shadowing effect behind it. Some systems offer line of sight, just 90 degrees going that way. Some of them are 180, some of them are 360 degrees. Our personal, we use a 180 and a 360 degree transducer to emit sounds. The 360, which is the Quattro dB, is probably the best answer for most things. Only time we would use a 180 system is like in your drinking water plant when you have your sediment basin comes through and you're pulling water off the top, where you get that long string algae, things like that. We use the 180s in between those. It helps cut down on the algae attaching to the troughs. Same thing like when you're using ultraviolet in the wastewater and it's coming down the trough. A lot of times people will put a mezzo next to that, and it helps keep those tubes cleaner. I know they have wipers, but algae seems to attack the end of those things and just stick there. First it's the biofilm that gets on it, and then the biofilm collects the algae on it, and it's just kind of a vicious cycle. You have to go in there and wipe them off, things like that. But anywhere from like a second on, you can use these things. Here's a drinking water. There we go. So in Olga, this is down in Florida, Lee County. We sent these systems down there. They bought them. This is in their clarifier. They were getting the buildups of the long, stringy green algae. The clarifier would have to be taken down annually to clean the algae off. Sometimes, depending on the buildup, more often than that. The installation of the control box and the head were very quick and simple. In these facilities, a lot of times, we'll plug them in, hang them right off of the walks with a chain, and that way they're easy to just pull up, wipe them off, drop them back in. Very, very simple to do. So within a couple of days of the install, small bubbles were observed all around the mats of algae, and that's where it's starting to break it up. It's trying to release the gases in it. It's trying to stop the matting. After 3 or 4 months of the units running, the algae had subsided dramatically. There was no longer string green algae on the walls, and the mats of the thick surface algae had diminished to a minimum. Other than large amounts of small surface bubbles, there was only assumed that it destroyed algae. So this is what I was talking about with your TSS going up. When it first starts to break up, there's much more particles in the water. So you will have a little bit of TSS, but it will drop right back off. You'll see the bubbles being released from the mats. It's where it's actually separating the algae from the biofilms, and the biofilms will go away. Anybody got any questions about this? What's up?
What's the average interval that you have to clean your transducer?
Yeah. Yeah, it's location based. In general, if it's thick sludge, things like that, I will say check it every week. Make it easy on yourself to do it.
Let him ask his question again. Can you say that in the mic so online can hear? Yeah, on average, how often do you have to clean transducers?
It's dependent on your location. Natural drinking water reservoirs, maybe once a month. Wastewater, it could be anywhere from every week to every 2 weeks. When you first do an install, I say check it after 2 weeks. and judge it from there. As this thing starts to work, as ultrasound starts to work, your cleaning times will spread out much more. So as you're killing off the algae, you're moving the biofilms out of the way, you will reduce the amount of times you got to clean it. But I say 2 weeks in a wastewater. I say once a month in drinking water reservoirs, holding tanks, things like that. In freshwater, once a month, maybe, because there's not a lot of buildup on them. I know everybody asks me, why do you got to clean them if it gets rid of the biofilms and the algae and everything? There is a small bubble around it that just does not do anything. As this thing projects out, like I said, it's a flashlight. It widens out as it goes. When you're talking like blue-green algae, we can cover 120 acres. Green algae, about 60 acres. Biofilm, 2.5 to 3 acres. Our best work with biofilm is within 2 acres. By far, that's the best area to cover. But yeah, the cleaning on is very easy. You wipe them off, throw them back in there. I've got a small scrub brush. I just go dunk it a few times, let it drop back in. And is that good?
Yeah.
Yeah. So, go here. So this is what we're talking about, placement of the heads. So I usually like to hang them off the walks, or drinking water reservoirs. I'll go hang it by the gates. That's sometimes an easy way to do it. They walk out there, they can pick it right up, wipe it off and do it. Sometimes we'll string it out towards the middle of it to kind of cover everything. Now, the results on the quickness that this happens varies. It depends on a lot of things. Like I said, the damping effect. Is it a natural body of water? Is it clay walls? Is it rock walls? Is it cement walls? Things like that. Cement walls are the quickest. You'll see the quickest results with that. Then rock, and then natural, whether it be clay or anything like that. But you'll actually see the rocks get cleaner. We got a company in Ohio that was amazed that the rocks were green all around their tiered water there, and it cleaned the rocks. Now that's where the TSS went up briefly, but it cleaned it right out. And they were amazed at how clean the rocks came out. It's kind of a neat thing to see. But you can hang these anywhere. I like to hang them in the middle, but in small contained areas like this, you can get away with something, right off of a walkway. I do that a lot of times when you're in drinking water or in wastewater. You can just hang them from the walkway. I like to say the easier you can make it to clean a transducer, the more often people will do it. So, and it's not that messy. It's just pull it up, wipe it off. Sometimes just paper towels will do it. So here we're going to talk about case studies. Aquarium Water, which is up in Connecticut. They supply 236,000 customers, 750,000 people in 72 cities. They're right on the border of New York and Connecticut. It's like 30 minutes outside of New York. It's crazy. But they had algae problems. So we went up there, and all of their drinking water reservoirs, they deployed our systems. They have several of our systems up there, probably 30. They were trying to limit the amount of copper sulfate they were using. So what we did is they set their limit for copper sulfate at 1 parts per million in drinking water. So they dropped off almost all of their chemical use up there. They are really, really happy with the systems. As you can see, here was some of the layouts that we did for them. That's something we can do for you. If you need a system or you contact one of our dealers or something, you can contact us directly or one of our dealers. We will actually do layouts for you and show you how to optimize where you would like to put these things. We can show you, we can say yes or no. Is this system right for you? I've had to tell him sometimes it's not right. If it's real heavy aeration, I'd like to try it some more. We might do something with that, but the heavy aeration is not great with ultrasound. Doesn't matter what brand you use, anything. The bubbles, it's the flashlight effect. It can't see through it. So when they got their solar rafts up there, they deployed them in 3 different reservoirs to start with. They worked out there. You can see where we had laid them out up there. across the top showing how much area you can cover with one of these. So the bigger areas, blue greens, then you have the greens, and then you have the biofilm there in the middle. After they deployed those, and within 14 days they started seeing results. Started dropping out reduced algae. They dropped their chemical usage. But yeah, they had great results up there. They've been using us since 2017 probably, and I'll put them on my route every year. I stop by, give them updates, check their systems, make sure things are working. And I do that with a lot of the customers. Like coming through, I'll say, hey, I can stop by and see you. I can see you, things like that. If we're on the road, we might as well stop and see everybody, right? But so here's another drinking water reservoir. This is over in Wilmington, Ohio. They have about 2 million gallons of treatment. They serve 12,500 people. The reservoir is 450 million gallons. They had blue-green, green, microcystids. They were having problems with it. So they've been using copper sulfate for years. Everybody loves to throw copper sulfate at it. But eventually it becomes resistant to it. So what we did is we put solar rafts in there, which is the floating power supply for the transducer. And it started to clear it up. They didn't see that green color anymore. They've reduced their copper sulfate. And let's see. And it was in September when it was probably the hottest out there. So your water temperature was way up. The algae's really trying to go. But you'll see results depending on the body of water. Sometimes as quick as a week. A lot of times when I test these, I go to local farms in East Tennessee, and where they have runoff and lots of geese and cattle and stuff like that, and everything runs down in the valley into these ponds. We'll let them get sludged up to where it's almost like Jell-O out there. And then we'll go put a system in and we'll actually test to see how quickly it can remove it. And a lot of times I can get them pretty clean in about 3 weeks. It's impressive. We had a small farm that was over there. There's a local electrical company owns it. And we couldn't even get the boat to move through the water. We had to pole it to get through there to actually push through the sludge. And what had happened was you had the biofilms that built up on grasses and stuff in there, and then the algae's attaching to the biofilms, and it was a mess. Within 3 weeks, we started breaking away the biofilms. The algae started dropping out. It cleaned up everything, and actually it's a great fishing pond now. You can actually see the fish in it. They're not dead floating on the surface anymore. They're actually swimming and creating beds. But it'll operate pretty quickly for you. I like to see, like in a drinking water or wastewater, it needs a little bit of time to work. It can work as quick as 45 minutes on some algae. Some algae need more treatment. Just like with anything, how much copper sulfate do you have to throw at it? How much oxygen do you have to produce in it to stir it up? But anything with about 45 minutes, you can start seeing some results as it's flowing through a plant. But at a drinking water reservoir, I like to see a couple of days of reservoir time. I like to see at least 3 days in there. That way it can really affect it, and it'll stop the biofilms. Like I said, the biofilms are what's collecting that algae, and it's making it hold in there. So if we can break that stuff up and let it flow on through the plant and be done like it's supposed to, that's great. Okay, here's where we're talking about how much it's going to cost you. So it will reduce your cleaning times, like I said. You won't have to put as much manpower out there. You don't have to do all these things. You don't have to pressure wash as often. It'll reduce the amount of times you have to clean the tanks. It'll cut down on your chemicals in your drinking water reservoirs. It will cut down almost all of your chemical that you have to put in there. You'll still have to chlorinate some in really peak times, but your algae problem can almost disappear completely. We have Seth at Aquarium Water. They only treat twice a year with copper sulfate, and that's when it's at its very peak. And when they were treating it once a month. It's just when your water temperature gets real high that you really have to make sure the heads are clean, make sure it's running good, and then you may have to spike it a little bit, but it'll not be anywhere near what you've ever had to do. They're easy to install. Like I said, most of them, You got a pole with a solar panel on it. You can run the cables right down. I trench them in so we don't run them over with the mower. We get a lot of those repairs every year. But run them right out there. They go to a float. They hang in the middle. You pull them in, wipe them off. With a pontoon style, usually that's in a larger reservoir, so you'll pull up with the boat, take a boat hook, grab the transducer, lift it up, wipe it off, drop it right back in. It's very, very easy. You can clean them in under 5 minutes. It doesn't take anything, man. You'll get fast results for it. Like I said, it'll be within 2 to 3 weeks you'll start seeing stuff change. Sometimes you can see it even quicker than that, depending on the damping effect, the maturity of the algae, things like that, how thick the biofilms are. So sometimes when biofilms are thick, it takes a little bit longer to release everything. But that's why I said you'll see that TSS jump, but it'll go right back away within days. But very simple. I install most of these systems in under an hour for the big jobs. Repair on them is very simple. Anybody that buys our systems, I'm the direct contact for anybody that has a problem. So if they have problems with the installation or they want to check on a power supply, things like that, I can usually have you back up and running within 72 hours. That counts sending you parts. So since we build everything in-house, we have control of that. So if I need to custom build something, bracketry, anything like that, we can do it within 24 hours. I can usually have it in the mail the next day. So I try to take care of municipalities very quickly. So you can start seeing some of these. Well, where did it go? Some of this technology can be very expensive. You can see where ultrasound and water quality monitoring would be $50,000. It can be higher, it can be lower. With my company, it's considerably lower than that. Even with like a 2 transducer system, with solar, you're talking under 10 grand. Well, right at 10 grand. But you can see how much typical for copper sulfates, things like that. You can talk 100, you can talk the world up on it. It could be anything, depending on how large your body of water is, things like that, how often you're treating it. Your water quality monitoring systems can be very, very expensive. You have to install sensors and pipes, things like that. We offer a system that actually floats out there and has a sonde unit hanging from it. We use Eureka probes mostly. They've been a good partner with us, and we can actually transmit the data back. You can see it, what your lake is doing at all times. You can also install these just about anywhere you'd like to watch your water. And they're very cost effective, but you can also see how expensive the chemicals can get over the years, how dangerous they are to work with. We were just talking earlier, the EPA. They were talking about permitting, things like that. We actually have an EPA number. Out of all of the ultrasound companies, I think we are the only one that has an EPA number. And when the EPA comes in to inspect us, we don't have any chemicals. The only reason we got that is because it's in the water. We don't put anything in the water. We're not adding chemicals, anything like that. So your permitting should be fairly easy. We use these in several places already in Illinois, and then talking with you this morning, they're talking about permitting for this. And I don't think we'll have any problem getting through it because we're not adding anything to the water. That's one of the tests that'll be just there. But all the systems will have the EPA number on them. So if somebody comes and asks you, about it, we're not throwing chemicals. We have an EPA number. We're actually listed as a herbicide. And when the EPA comes in, they look around and goes, "Where's your chemicals?" And I go, "We don't have any, and this is how we do it." And they go, "Oh, okay." And they just sign off. So if you had any questions about any of that, we can get you through that. Do we have any questions about the cost and operating of these systems? Yeah.
Do you recommend these are only operated because we have colder temps in the winter? Do these only need to be operated in the kind of from the spring to the fall?
Well, with algae, you don't get as much algae in the winter. So when that water temperature rises, if it doesn't freeze solid, I run them year round, 24 hours a day, year round. Power consumption on these is very, very low. Our owner, engineer, is very big on efficiency. So it's like running a 60-watt light bulb all day. It's very low cost to operate. And if you're talking solar, it's nothing. But the AC system's it's about like a 60-watt light bulb. So you're not pulling a lot of power. You don't have to set a dedicated circuit, anything like that. You can plug them right in the wall. But I run them, unless it freezes solid, leave them out there. Leave them running. It'll help with the biofilms. They don't want to accumulate, which traps algae. You know, we can still kill the algae that's trapped, and as soon as the biofilm releases, it'll release algae. It'll sink to the bottom. But year-round, run them. You should.
I know you've also, I know we're really talking more, this is kind of focused on the wastewater, but you mentioned some of the natural
Yes.
reservoirs. Have you found any effects on aquatic life?
None.
Or other?
There's several case studies I can show you on our website. We've been tested with Cornell University did a test on wildlife with it, and we have not affected anything. We actually had some down in Florida that were around manatees, and they did not seem to notice it. It's a federal law down there, well, federal law that you can't mess with the manatees. And even if you change their habits, you know, you have to pull it out. So we went down and did a test, and they had no response to it. So I haven't seen any response out of fish. You can see the Cornell study. There's several other studies that show because of the power we're using with our frequencies, it's not creating a cavitation. So we're not messing with things. You know, it's a low power, but you'd be surprised how far sound travels in water, especially these frequencies we use. We use 20K to about 220K, and it's outside of our hearing, but at the wattage we're using, which is about 18 watts of power, it travels great through the water as long as there's no obstructions. And you can hear these things like we have a meter I go out and test with. We have a sound pressure level meter and then an audible meter. And you drop a microphone in, you can actually watch the frequencies and watch the intensity of them. And some frequencies travel farther in water than others. And that's just the way it works. But very, very easy to take care of. If you put them in there, as long as that pond or anything is not frozen solid, leave it running. Even if you get a light skim of ice across the top, you know, that half-inch stuff, you can leave them in there.
I have a question for you. Have you guys ever used this like in a wastewater effluent channel?
Yes. You can put them in the channels. The problem I have is you can keep the biofilms down, but the algae won't. It's not enough stay time. With the sound pressure changing so much, the biofilms will not stick to the walls, things like that. That's your big savings on that side of it. Coming out of the plant, you know, you want to reduce your algae, and get it finally cleared up to be released again. That's mostly where we use these. We do use it on the channels. It'll just the biofilm factor of it. Coming out, when you're reducing algae, that's where you really want to use them. The lagoon styles are best.
So I know you talked about chlorination. How does this system work? Like if you're using sodium hypochlorite and then bisulfite, does it have any effect on the equipment at all?
No, these plastics that we use are designed not to release anything into the water. I've got systems that have been in the water 6-7 years, come out, just wipe them off. It's pretty slick the way it's a mirror finish is what they call it. So nothing will attach to it. If you get some scratches in it, that's where stuff will want to stick. But outside of that, yeah, it's just no chemicals are going to get in there. It's the fully potted system. So if something does happen, say it gets dropped, it gets cracked, something like that, the circuitry and the transducer crystals, we use a piezo crystal on the inside, are actually fully potted. So you're not going to leak any water in there. You're not going to create a problem. Like I said, it's low voltage. We're using 40 volts DC, runs down to the transducer. So it's considered low voltage by UL standards, CE, things like that. So you're not going to shock anybody. It's less than an amp of current being pulled. And as soon as the power supply sees that head is not attached anymore, it shuts off. It'll give you the warning light and say you're done. Because we don't want to, electrocute anything, hurt anybody, but it's very low voltage. You'll be able to, like I said, you can run it on a wall socket right here and just no dedicated circuits needed. Let's go. So that's okay.
When we talked before, you discussed how your unit cycles through the different frequencies.
Yes. So
I don't know if you want to explain
Yeah.
that a little bit.
So we use about 2,500 different frequencies and their harmonics. We use a 0.4 second burst every second. Once it runs through the cycle, it actually does a start pulse again and starts those frequencies again. So it's about 40 something minutes, then you get to reset, it starts again. It runs 24 hours a day this way. Each one of those frequencies we've tested and tested and tested to make sure that that is a critical resonant frequency to be used with algae or biofilms. Some companies will say they use 10,000, you'll hear 4,400, you'll hear all kinds of different frequency numbers. It's not as important as them being the correct frequencies. The way we even stack our frequencies is we run in 2 different bandwidths, and then we'll actually jump between them and actually sometimes layer them on top of each other. So depending on the size, things like that, those frequencies are very important. The frequencies do not bother fish. We do use them in like dive centers. So you have divers down there with them. They can hear them sometimes, certain frequencies they can hear when they're in their mask and underwater. Most of the time they don't hear it. We've used them in swimming pools. The owner has one in his pool. And his daughter says she can hear it, but nobody else can hear it. I don't know. She's probably the youngest. Maybe she's got better hearing. But nobody else feels it. Nobody hears it, things like that. So it is safe, but the frequencies are very, very important that they are the right frequencies. A lot of companies will tell you, yeah, we're making noise. Some of them are making music, and you'll listen to the frequencies. Some companies will tell you that they only need 75 frequencies. I don't know how you would ever say that because, the damping effect, the distance, the size, what's in the water, is it salt water, is it fresh water, how much phosphorus is in the water, especially down south where we are, things like that. It changes every bit of it. So you need to actually have a pretty wide span of it. But we've had great results, especially with the CO5 program. So, anybody else? Come on, I got to fill 20 minutes.
Do you have any case studies with wastewater lagoons and the effect on the discharge?
Yeah. So like, who's our buddy up here? Ron Miller? Is it Ron Miller? Yeah. So they've been watching him, and it's actually dropped his TSS way down. We've done a lot of wastewater. I can send you some studies, actually show you how much chemical you're having to use, things like that. But we are monitored by the state and federal government. So we do have studies, and we can send you profiles of what we've done, anything like that. Anybody else?
Does it kill duckweed?
No. I wish. Not millweed either. It just, I really wish we could control that. I got a guy up north that has mystery snails in his lagoon, and they're like this big. And he was like, "Can you kill off the snails?" And I'm like, "We tried, but yeah, that's." I really wish we could control that. We'd be multi-billionaires probably. But actually, sometimes that's good for you in the lagoons because it actually kills off the sunlight, which kills the algae underneath it. So sometimes you can just wipe that back, and you'll see it's clear. But yeah, I wish I could do something with it, but I can't.
There's a dye supposedly.
Yeah.
Yeah, but it doesn't let the UV light through. It's supposed to get it up and down whether it works.
Yeah, it's like putting sunglasses on algae. We get a lot of people using dyes, things like that. And it's just dropping the turbidity of the water. Sunlight doesn't penetrate as far anymore, so the algae can't grow. So that is a way of doing it. You can shade it out. But that only lasts for 2 weeks, 2 or 3 weeks before the dye all settles out. And then your reeds around your lagoon and everything are kind of blue, and some of the fish turn blue. Not great for the environment, but they say it's safe. Any other questions? That about it? Sorry, that's all I got. But if you have any questions, you can contact us. It's hydrobioscience.com. More than happy to answer any questions. Send us your profiles, show us where you're at. We'll tell you if we can help you or not. I don't like to take on jobs that I don't think we can work in because it does give it a bad name. And we want to keep our name really good. Thank you very much. Sorry, that's all I got.
We've got some association stuff and transfer and load up presentations for the next presenter, and
Okay.
it's all good.
Okay. Yeah.
Jason, do you have your presentations? We can go ahead and load.
We're gonna take a short break, and we'll be back in 5 minutes or so.
That's on then? Okay.
As long as you don't hit that button, you're good. And yeah, you put that in green.
Okay, we're going to get started back. Again, this presentation, all three of the presentations today were given at our Effingham conference in February. These upcoming ones, I know the first one, I used to operate a plant like this retrofit in Farmington, Missouri, and I know it would be of particular interest to some of the people, members of the group that have similar plants.
So you want to do Farmington first? You want to do treatment plant first or pump stations first?
You can do pump stations
We're
first.
going to do pump stations first because
Okay,
that's
we're
what's
gonna do
keyed up.
pump stations, then the Farmington, Missouri
Second.
study. So,
Perfect.
thank you.
All right. Just between the flags. All right. Good morning. My name is Mark Mayer. How are you, everyone? So we're going to do two presentations today. One is on pump stations, and we're going to talk about pump stations, a little bit about the hydraulic design and focus on that, but also about the equipment and what it does. How many people have submersible stations? I gotta believe everybody does. So in that station, in a submersible pump, which is primarily what the marketplace has gone to, a lot of pumps are essentially the same almost today for smaller pumps. Larger pumps are some differences, but in a submersible pump, we have the following things. We have motors, we have bearings, we have seals, and we have an impeller. So with that being the case, what we focus on is we say, okay, let's talk about motors first. There's oil-filled motors and there's air-filled motors. Regardless of what you have, all those motors have to get rid of the heat. What happened? Whoops. Sorry about that. How did we get there?
You went about 10, real fast.
All right, we're done with this presentation. Okay, I think what I did was, all right. So all motors are either going to be oil-filled or air-filled, but we got to get rid of the heat. In today's world, back in the day, we didn't have everybody have inverted duty rated motors, which are VFD motors. Most motors today are all Class F or greater installation on motors. So therefore, you can hook them up to a VFD and therefore operate them. Bearing life. So in bearing life, minimum would be 50,000 hours. Most manufacturers of Flight, Sulzer, KSB, those guys have 100,000 hour bearing life usually in their pumps. Some of the smaller pumps don't, but they're not going to operate up to potentially 24/7 every day from that perspective. Seals. There's a big difference in seals today. The smaller pumps have usually carbon ceramic seals, which are pretty soft. So if you're operating in a gritty application, that's going to scour pretty quickly, and therefore it's going to fail relatively soon versus a tungsten carbide or a silicon carbide seal, which are very hard. But when you install a silicon carbide seal or a tungsten carbide seal, what is it? It's very brittle. So if you're going to change seals, you got to be very careful. You don't get that thing a little cocked when you put it on the shaft, because what will happen is you'll break it. And therefore, you're going to shoot about $2,000 right in the butt. So therefore, you want to be really careful when you do that. But a carbon ceramic seal is pretty soft. It'll take some of that adjustment as you push it up on the motor shaft. So therefore, then the big difference comes in impellers, which we'll talk about in a second. But every motor manufacturer, every pump manufacturer has kind of an application. What we do as a supplier is we talk about the bigger the pump, the better the company's got to be. In the submersible marketplace, there's 3 European companies between Flight, KSB, and ABS. Those guys have probably the most pump sales in the world, in my opinion, relative to everybody else. But once you get below 20 horsepower, you can incorporate almost everybody into that business. The pricing is becoming much more of an issue, as well as you don't have to have such a big investment into that station. So we're not talking about 1,000 or 500 horsepower or 300 horsepower pump. It's a 20 horsepower pump. You can swap that out pretty simply. And we all have different programs that we can use. So in the different programs that we use, you don't necessarily have to pick the most efficient pump, which is where typically most programs that we have will go to. So we're going to talk about system curves and pump curves and those types of things a little bit in this conversation today, and GPM. So the first thing we talk about is how many gallons a minute does that station need to run? What's the head? What is the brake horsepower? What's the cavitation? How many people have ever heard of cavitation? Yeah? How many people have seen it? Okay? We're talking about static. We're going to talk about solid handling size and all that type of stuff. So the first thing is how many gallons a minute do we need to pump? So in the pump world, we can have a rule of thumb. We got to make sure that we have enough capacity for whatever we're going to pump to make sure that that thing's going to get the water out of the collection system. Regardless of what the head's going to be, how much is it we're going to get out of there. Therefore, we typically look at 1 GPM per home. 1 GPM per home. For every home, we typically say we're going to have about 3.5 gallons, 3.5 people in the home, 100 gallons per person per day, roughly. And therefore, we take the number of homes that we're going to maintain times 3.5 times 100. It's going to give us a GPM for 24/7. We divide that by 1,440 plus times a peaking factor. That peaking factor is going to be like everybody waking up and showering at the same time. Everybody going to go do clothes at the same time. All those things happen at the same time, or some I&I issues. Therefore, we have a peaking factor of that pump station. So the bigger the thing it's going to be, the less peaking factor. For example, in the city of Peoria, you might have a peaking factor of 2.5. You get a small community out in rural areas, it might have a peaking factor of somewhere between 3 and 4, just because there's more variability in smaller communities than there is in larger communities, even with a rain event. So we talk about TDH. In TDH, there's 2 conditions that we got to worry about. First is static. Once we put the pipe in the ground, static is static. It's not going to change. The second one's going to be dynamic. The dynamic is going to change based on the amount of water we're pumping through that pipe and the type of pipe. Pretty simple explanation. We got one going up the street. We got a wet well on the left. We're pumping it straight uphill to the wet well on the right. That static is going to be 100 feet. The static is from the bottom, I always take it from the bottom of the wet well to the highest point in the forced main, or in this condition, it's the top of where we're going to go to gravity sewer from that point, or 100 feet. In this condition, I've had some engineers tell me it's got to be from the top of the wet well to where the highest point. They would be not right. If we look at this condition, we could say, okay, we got a force main going up like this, then our highest point is above our 1100. So we got to be careful of all that. What do we put at each top of these little rise points? We put air relief valve. Why do we put an air release valve? So what is airlock? Right. What happens is that air is going to always rise. You're in the tub, you're in the pool, you blow air out, it's going to go up. What happens is that air is going to stay at the top of that pipe, and therefore that pipe's going to become smaller and smaller and smaller over time. When it becomes smaller and smaller and smaller, that's going to increase our head because we have less amount of pipe diameter that we can pump through that particular pipe. Therefore, our head goes up and our pump doesn't do its job. So water is always non-compressible. As this water is non-compressible, we can push that water up through there. We can release out any air in the collection system that the pump station is pumped up, and therefore it's going to maintain and just keep going like stuff through a snake as it goes up. So as we look at examples to say, okay, this particular one, this is a dynamic curve. Why is it dynamic? Anybody know? Why do we call it dynamic? It's dynamic because it can always change. What can change in that system? The things that can change in that system are the amount of gallons we're pumping. What else? Condition or the type of pipe it's in the ground. So say, for example, we're pumping through an old cast iron, ductile iron pipe that's been in the ground for 100 years. What's that thing going to look like? It's going to look pretty, old Barnacle Bill is what we usually call it. It's going to have a whole bunch of crap stuck on the side, and it's just not going to look very good. So as we pump through that, what's going to happen? That friction is going to be higher because it's not smooth. But a brand new PVC pipe, that's going to be as smooth as a baby's butt. And then what's going to happen is that stuff's going to go through there like a rocket with less horsepower, less energy that we have to put into that pump, in that station to get that water out of there. So therefore, when we look at stations, we look at two different C factors. In our business, in the pump world, Illinois DEP says EPA, we've got to design our stations for a C factor of 120, which is a piece of PVC pipe or a piece of pipe that's been in the ground for 20 to 50 years. Okay, we can do that. But we also, as a pump suppliers and designers, we've got to understand that we just can't do something right at the edge for horsepower because we're going to exceed that pump station volume at the very beginning. Why are we going to exceed that pump station volume? Because our friction is lower because we have a higher C factor. A higher C factor means really slick pipe. Lower C factor, a lower number, means a really Barnacle Bill pipe. By doing that, then what happens is we are going to exceed our station. So what's the first thing you guys do when you get a brand new station? You put it in service, and what's the engineer, what's the city guys, and what's everybody do? I want to make sure that we didn't screw up. So we do a pump down test. So say, for example, you got a wet well that's 8 feet deep, or let's say 15 feet deep. Pipe comes in the middle at 7.5 feet, and we fill it up 10 feet. How do we do a pump down test for that? Can we? What is a pump down test? Pump down test is when we time it. We turn the pump on, force main's full. We turn the pump on, we time how far it goes down in a certain diameter and how much volume we're pumping in a certain amount of time. So time versus volume gives us GPM. But what's one important thing about a pump down test you got to be careful of? Anybody? All right. You got to do it below the invert coming in. Because you do it above the invert, what's going to happen? All that force main, all that gravity sewer is going to be filled up with water. When you fill up the gravity sewer with water, when you pump it down, that you're pumping down the whole lake as compared to a little pond out the outside that you want to focus on. So be careful of that. Some people get caught up in that when they're doing pump station pump down tests. So they say, oh, shit, we're only pumping 10 gallons a minute. It's supposed to be doing 1,000 gallons a minute. Well, what's going on? Your pumps stink. Well, once you figure out that, well, maybe this 30-inch diameter gravity sewer we're pumping out for the last half mile is all full of water, we're pumping that out too, maybe that has some conditions of what we're doing. So when you're doing a pump down test, make sure you're below all you have a known volume you're doing in that wet well so that you're pumping that volume down. It's a true representation of where you're at. But when you always do a brand new pump station, brand new force main, what's the first thing you know you're going to do? You're going to exceed that GPM because you're going to have pipe that's going to be slick as snot versus some 50-year-old pipe. Your C factor is always lower your C factor is higher, your head loss is lower. Therefore, we're going to be operating at a C factor 160, not C factor 120. So we're going to have a lower head on that pump. But to get a TDH to that pump, now we know we know what the volume we have to pump. Now we're going to add our static and our dynamic that we're going to do to give us the TDH. So how many people call their lift stations by their real name, what they should call them? How many people call them Fourth and Main? Or by the street name that they're at? Yeah? What should you do? You should say Fourth and Main's pumping 700 gallons a minute at 100 foot ahead. Therefore, you'll always know, because you always have some records somewhere on where you're at and what you're doing. But pumps always give you a gallons per minute at a certain head from that particular point. So we go to our computer, we go and plug in our computer, and we end up with several curves. The first curve we have starts at 100 feet. Why does it start at 100 feet? Let me see, is there a pointer on this thing too? I don't know. So why does it start at 100 feet? If we put a pressure gauge on that pump, why does it start at 100 feet? That is our static head. So how many 100 feet is that in PSI? How many feet are equal to 1 PSI? Close. 2.31. So if that's at 100 feet, or let's say it's at 100 PSI, that would be 231 feet. We aren't going to get 100. We aren't going to get 231 feet in our normal conditions for what we do. We're going to be somewhere less than 100 feet, mostly on static, in usual conditions. But why does that blue line go up at a parabola, if you will? It's not straight up at a 45-degree angle. Anybody? The reason why it is because the friction in that pipe, that's a representation of friction. The faster we pump water through that pipe, the more friction we have, just like driving your car down the highway. The faster you drive, the more friction you have. Therefore, it takes more energy to get there. Same thing here. You can only pump, in our business, we have a saying, we call it, you can only pump so much poop through the pipe. So that friction is going to go up, not at a straight line, but at a parabola, based on the velocity of water through that pipe. What's the line coming down, the blue line coming down from the upper left where it says 182 down to the very bottom right? What's that? Curve. That curve is the impeller curve. So for any one pump operating a specific any pump, any impeller is going to have a specific performance. Regardless of where you put it, it's going to have a performance. Therefore, what happens is that where the system curve, which goes up to the right, and the pump curve, which goes down to the right, where those cross, that's going to be the exact duty condition of where that pump is going to operate. So the computer is going to give you that, depending on how you select your programming on your computer, but most are going to be efficiency-wise. The top selection is going to be what's the most efficient pump. Regardless of solid size, that's the most efficient pump that it's going to have. Therefore, in this one, is going to be efficiency of 67%, which is pretty good. Off to the right, you'll see that that line goes dashed. Why does it go dashed? That impeller's spinning. If we don't have quite as much head on that, what's going to happen? That pump's going to slide out to the right on that curve. When it slides out to the right on that curve, it's going to require more horsepower. When it goes to more horsepower, it's going to go dashed. Therefore, whatever motor that we selected on that impeller curve, that motor can't handle that duty condition. That's why it's dashed. So how many people have an amp probe? So you go out there for an amp probe, what do? You stick the amp probe on the thing, You look at the full load motor on amps on the pump, and what happens? You're operating at 20 amps. But full load on the motor is only going to be 15. You're operating up in that safety factor. That's never a good thing. Some engineers design it where you can operate in safety factors. We never supply stuff in safety factors. I never want to do that. So what happens is that all your motor controls are going to start tripping out at 20 amps or 15 amps or lower or higher. Because over time, that amp is going to heat up. You want to protect that motor. Let's design something properly. So that's what all these different lines on the curve mean. What's that very curve to the left where it says application curve, the green thing up to the left? It's a cavitation curve. You don't ever want to operate to the left of the curve because the water can't get out of the pump. And then what happens is that you will cavitate that impeller. And by cavitating the impeller, what's cavitation and what's it look like on an impeller? For people that have said that it looks like they've seen a cavitation.
I got pictures on my phone.
Well, there you go.
Like pitting and stuff?
It's pitting, absolutely. Depending on how badly you operate to the left of the curve or closer up to the left where it says shut off, at the very left at 0 GPM at 182 feet on this pump station, the closer you get to that, the worse cavitation becomes. And therefore what happens is there's air in the water, and it'll start to pit or explode right on the impeller because of the vapor pressure inside that impeller, trying to get the water out of that pump. It just doesn't work. Therefore, you want to make sure you have something that's going to operate easily and well, regardless of the conditions. And you never want to operate to the left of that curve. You don't even really want to get close to it if you don't have to. But usually conditions of lower flow, higher head, those are areas that you've got to be careful of when you get to be, 50, 100 gallons a minute at 75 to 100, 150 foot ahead. Those are conditions that you've got to be really careful of. So when we do our C factor, when we do our pump station curve on our computer, we look at two different C factors. We come up and say, okay, the left one is the specified one. That's typically what the engineer is going to give us as a supplier. Hey, I want you to do 700 gallons a minute at 150 foot ahead. Perfect. So we do that. We pick a pump, and let's say that pump is 20 horsepower. Perfect. We go out there, we start that station up, but our brand new pipe is going to give us not 150 foot, it's going to give us 140 foot. What's going to happen? We're going to give you more GPM. This is actually the condition we're going to give you. It's 810 gallons a minute at startup at 145 foot ahead. If we took a different motor and we had a dash line right behind where that big red dot is, that motor's going to what? Overload. And it will burn up. So what we do as a company is anything less than 20 horsepower or so and down, we just give you that line all the way being blue, solid blue. We call that non-overload throughout the entire curve. Regardless of what the specs say, unless there's a definite need like horsepower limitations or something like that, we want to make sure that regardless of where the station is going to operate, it's going to perform well. And even if the engineer or somebody made a mistake or the pipe went in differently or whatever the case happens to be, we run into conditions where the contractor had to go deeper for some reason. Or the engineer had to reroute a pipe because they couldn't access Mrs. Smith's property and they had to go over to Bill's property to go around. It was a little bit higher. Something along that line. Things change. We may not always know about those changes. If we do not know the entire curve, we can go back in there and put in a different impeller and be safe. So then all we have is the cost of impeller versus a whole new pump and controls and everything else. It's just a simple safety factor from that perspective. So this is a condition of pump 1 and pump 2. This is a 2-pump station, 2 pumps going into the same force main. Same conditions happen. The system curve doesn't matter if it's got 1 pump, 2 pump, 3 pump, 4 pump. It doesn't matter how many pumps it is. System curves are all based on what's in the ground. So therefore, we're starting at 100 feet and we're going up to the right. So what happens is we have a duplex station, and in that duplex station, usually we get toad strangler rains like we've had the last week. What happens? How many people have SSOs in their collection system? What may you do when you go out there? You go out there and turn the pump on hand and turn the second pump on hand, right? Yeah? No? No? Well, some people do. And what happens is the second pump turns on hand and we get a call. Hey, Mark. Yeah, Frank, what's up? Hey, your pumps stink, man. Why do you say that? Well, because I turned the second pump on and I got barely anything more out of it. Oh, okay. That's not surprising. Well, your pumps stink. I ought to get twice the flow. And therefore, I get rid of my SSOs in my collection system. Well, that's not true. The reason why that's not true is everybody in this room and online knows today that it is the system curve that controls that. For this particular station, we turn that second pump on, we're going to get a grand total of 110 gallons a minute more volume out of that station. Not a bunch. If we're getting 4 inches of rain a day, 110 gallons a minute is a drop in the bucket. But that's a critical factor, understanding how long your force main is, what your C factors are, and that's the reason why. It's not the pump's fault. It's the TDH's fault. Because, you guys can remember this, you can only pump so much poop through the pipe because the pressure goes up. And if the pressure goes up too high, you can't pump any more poop through the pipe. So remember that. If there's any that you remember out of this whole thing, remember that. Because if it's a short force main, you could pump a lot more flow. Long force mains, that force main is going to be your limiting factor on your TDH and what your pump capacity is, because that impeller can only put out so much water. As we go up, this is that station right there. One pump is the blue line P1, P2 is pump 1 and pump 2. But you can see that friction goes way up. When it goes way up, that pump, that centrifugal impeller, can only do so much. And in this case, it starts to cavitate off to the left. So if each pump is doing if one pump does 700 gallons a minute, we turn 2 pumps on, and we're pumping 810 gallons a minute up that station. How many gallons a minute does each pump do? 405 gallons a minute. So we're doing 405 gallons a minute at 168 feet. We're pumping way back here to the left. See that yellow cavitation line? Each of these pumps is now cavitating. That's not a good scenario.
So not only are you not pumping more poop through the pipe, you're destroying your pumps.
Absolutely. So if this condition went on and on and on, you'll turn your impellers into Swiss cheese. So important is impeller selection and understanding what's going to happen. In that station, doing an extra 110 gallons a minute has no benefit to anybody, virtually. It's going to actually do you more limitations. But pumps are always not based on volume. you get enough volume out of it based on the head that they produce against. So if you go back to this curve here, that one pump can do all the way out to 1,500 gallons a minute if it only had 60 foot of head on it. But that same impeller will do all the way up to 1,500 gallons a minute, all the way back to 700 gallons a minute, based on the friction or pressure it needs to generate. And by doing that, that's how you understand pump curves. But pump curves are always based on pressure. We talk about volume, but we have to talk about volume and pressure at the same time to really understand what's going on with that station. And as I mentioned earlier, we as a company, anything less than 20 horsepower, you're going to get a full, not only the entire curve motor. Controls are essentially the same price, whether it's a 10 horsepower pump or a 20 horsepower pump. They're the same price. Therefore, unless there's some limitation there that gets alerted to us by the engineer, but usually there's not from that perspective. Wires that big versus that big, it's the same price. We're not talking about wire that's the size of your thumb or anything like that. Then we got to talk about cavitation. So most people are aware of discharge cavitation. So what's discharge cavitation? That is the ability of that pump not to get that water out of that pump. That's all the stuff to the left side of the curve, that big yellow dashed line that we talked about. You never want to operate over there. There's also a thing that called suction cavitation that people sometimes see, but they really don't see sometimes. It just depends. How many people have dry well, wet well stations? Influenced to treatment plants or anything like that, which is really where we see this coming up, or in a collection system. So we call it suction cavitation, or sludge holding tanks, or decant tanks, where the decant elevation may be 4, 5, or 6, or 10 feet in that sludge tank. So you gotta be careful of that when you select your pump. Now this pump usually doesn't run very much, but what happens is that when it's full, you have less head because we're only pumping up a little bit, versus when it's down all the way to the bottom, when you shut the pump off, the head comes back. So what happens is most engineers, these are all slow operating pumps, they have a very flat pump curve. Well, most engineers say, all right, we want to pump at this elevation, but they ignore that elevation up top. And when they ignore that elevation up top, then we slide out to the right, or we have lower static, because the static does change on those. That gets to be a big issue. So when we review pumps, we review 1 and 2 pump in operation. If it's a triplex pump station, I just had this discussion yesterday with a very large engineering firm about a quadplex pump station. They want 3 duty, 1 standby to pump 15 MGD of flow. And they want to do a very small force main. They want to do a 20-inch force main, which the velocity is like 9 feet per second. The velocity in that pipe is just phenomenal. They're like, yeah, we can do that. And I said, no, you don't want to do that. Because all your elbows, everything else will wear out from that condition. I got 350 foot of TDH on this pump at 15 million gallons a day for these pumps. Needless to say, we're talking about 2,000 horsepower, something like that. Some stupid number. So we got to worry about low flow, high head applications for cavitation. We got to understand what we're doing. How many people have heard of a recessed impeller? A vortex or recessed impeller? For small pump stations, I believe this makes sense, but we're going to talk about the different impellers that are options. So here is a vortex impeller on the left, a 2-vane impeller on the right. Well, I'll show you videos here in a second. You'll see the vortex looks like this is probably the wrong time of year to say this word, but it generates like a tornado inside the volute. I'm from Kansas, so I could say tornado. But it has a tornado inside the volute, but the solids never go through the impeller. The impeller on the right has a 2-vane impeller pump to it. The solids come up and go out through the 2 vanes, and they're 180 degrees opposed from each other, so it's completely balanced from that perspective. You'll notice this guy on the right has a wear ring. The guy on the left has no wear ring. So the guy on the left is not quite as efficient, but not as bad as you think. The guy on the right is the most efficient pump that's available to pump wastewater because it's like the oil rings in your car. It's a great application. But this guy here, solids come in the bottom, up the bottom, get into that tornado and gets puked out the discharge side. Less plugging, less everything in that pump. So there are 4 pumps, impellers that are available. Now that we're down from the motor, through the seals, through all that kind of stuff, let's get to the impeller discussion. Talk about the impeller discussion. We have the 2-vane impeller, which is the multi-vane. Some manufacturers do 2-vane, 3-vane on really big pumps. One of our competitors does a 5-vane impeller pump. Probably not the choice that I would make because solids that come up, rags that come up, instead of a 180 degrees, that rag could come up, go from one side to the other. You take 360 divided by 5. That's less than 90 degrees apart. That rag is going to come up, get stuck in between 2 vanes, and plug that pump. 180 degrees, there's less of a chance of doing that. With Vortex, there's no chance of doing that because there's no vane that really we worry about. So we have 2 vanes, we have a single vane of pump, it kind of looks like a one-armed bandit at a slot machine. That guy's a great pump, but it has to be operated in a very narrow condition because it's balanced, because it only has one arm out there. It has a Vortex impeller pump, which is the very bottom left, and then a screw. A screw pump's a really good pump, but it has limited operations based on what you want to do. Let's see, I don't know if I can do this or not. Let me see what this works. There we go. So the top left is a screw. How many people have screw pumps at their influent pump stations, at their treatment plants? So screw pumps are like 4, 5, 6 foot diameter screws, Archimedes screws. Pretty efficient pumps. They'll handle everything. That's what that pump does, the very top left. So the solids are the 3-inch diameter solid that comes up through the ball, illustrated by the ball. It comes up and goes in and out. High volume, relatively low head application pumps. Let me go back here. And I almost had it. Can you push the,
I tried it.
didn't work?
You go back to another slide and then.
It has to sit for so many seconds, and then I think it just takes off on its own.
All right, well, wait. So a Vortex impeller pump, you can see there's nothing beneath it. There's no wear rings, there's no nothing else. That just generates a big old tornado in the station. One in the upper right is a single vane impeller pump. The single vane impeller pump will handle rags and other things. Soldier called it their contra block impeller, at which time, did they work? Oh, there you go. Solids come up and they get discharged by one impeller. Good impeller, good efficiency, not quite as much as the 2-vane, but there's no opportunity for a rag to come up and get stuck in go out both ports at a 2-vane. And that, sorry about that. Then we have the Vortex and screw. We also do, how many people have grinder pumps in your systems? Do you like them or hate them?
Our group's pretty good most of the time. Sometimes we have to put them out.
Okay.
We got one in our scum pit too.
Okay? So grinder pumps, there's a couple different ways to do grinder pumps. There's an old style of grinder shredding rink, which is the bottom. Then there's a new slicer dicer, which is the top. The new slicer dicer is a much better product than the old one, because what happens with the old one, you get material like this, the grinder shredding ring. This has been installed at a dog pound for a week. You can see how much it has gone and routed out the side of the shredding ring, and it's just worn out. And a grinder pump requires that torque to get operational so it can operate and cut that material that might be stuck halfway in and halfway out. So the new slicer and dicer, that's the video, will operate really well because stuff doesn't get stuck up in and out of it, halfway in, halfway out. And there are variations of this on the marketplace. Excuse me? Does it? Yeah, we put these in schools, nursing homes, where we would never suggest people install a grinder pump at a nursing home, but some engineers do and some developers do. This is the only one that's worked. That style of impeller and cutter. So by its back swept design, it'll keep it clean, but yet pump all the water out and pump and eventually get all the stuff chopped up. So it does a really nice job. So that's grinder pumps. So if you have a 4-inch diameter pipe or bigger, what type of pump should you use? Should you use a grinder pump? No, don't use a grinder pump. Do yourself a favor. Okay, if you're going to have a 4-inch diameter solid or 4-inch diameter pipe, use a non-clog or a solid handling pump. Grinder pumps may be a little less expensive in their capital costs, maybe, but they are much more higher on O&M cost. Therefore, you'd better off using a properly designed, properly installed, non-clog or solid handling pump for anything that's 4-inch and larger. So when we talk about 4-inch and larger, this is a Vortex impeller pump.
What you're looking at is wastewater being taken to a treatment plant. Just a perfectly normal pumping station doing its job, fitted as they so often are with a small submersible motor pump. A KSB product of which there are thousands all over the world. But what do you think will happen if objects get into the pumping station? Objects that have absolutely no business to be there, but often turn up in wastewater. Objects like a cleaning cloth, a wipe, a sock,
the flushable wipes.
or a rubbish bag, or even a glove. And why not a pool ball? This one's plastic, but still. And a bottle, a drinks can, and to cap it all, a shoe, and some cable, made of metal of course. What will a pumping station do to them all, and vice versa? Would you like to know? Want to look? All right, then watch carefully. Let's start at the easier end. The cleaning cloth, the wipe, the stockings, danger time, the rope, tricky, the rubbish bag, a handful of problems, the glove. Great balls of fire. Anyone for ball?
Ignore that it's a German company with an English moderator, so.
And the cap. To top it all off, here comes the shoe. Looks about size 10. And bringing up the rear, smiling all the way, is that really nasty cable. And here it all comes out again. All this swimming rubbish is left untouched, thanks to the impeller's large free passage. So what, you might say? Well, that's really important, not least for the KSB pump. Because it doesn't waste effort and chomp up the flotsam, the pump keeps its hydraulic efficiency and the motor doesn't get overloaded. It's also important for the whole process. The rubbish cannot clog up the works. Cleaning the screen is simpler, filter capacity remains as it should, and treatment of the wastewater is easy.
So as you can imagine, this pump pumps everything, okay? Two design things you got to be careful of, though. All right, how many people have ever had a pump that's just plugged up? Yeah? Okay.
The two main, like you said, pumping uphill, that I've had it done where it clogged up. Somebody put something really huge in there, and what I did, reversed it. It actually come out.
You got lucky.
Got lucky.
You got lucky. All right, there's two things you got to be careful of when we design stations. So normally this happens in the areas that are growing. For communities outside the major metropolitan area, especially, or developer areas where they're like, hey, we want to put this in now, but we have more stuff coming in the future. So they'll put in big pipes. So they'll put in a 6-inch riser, put a 100-gallon minute pump station, 100-gallon minute pump on a 6-inch riser, 6-inch check valves type stuff. So we all know what's the velocity in our force main. What's our minimum velocity in our force main? Anybody know? 2 feet per second, okay? So over decades and decades and decades, we figured out that 2 feet per second will keep all of that debris moving in a force main. But if we're pumping straight up out of our wet well and through a check valve, that velocity needs to be probably 4 or 5 feet per second. Because what happens is your check valve is going to be restriction, right? At which time, if you're trying to pump this rag or this flushable wipe, you got to get that flushable wipe into the force main. But and that check valve goes like this at 100 gallons a minute, it's only going to open up 15% of the way. What's going to happen is all that debris is going to get stuck behind that check valve down through the pump. So it's important to understand when the engineering firms design pump stations, they need to say, all right, we know that we're going to do a 6-inch pipe, but we only have 100 gallons a minute we're going to actually have now to pump. But we still have to design the pump station to be able to pump that 300 gallons a minute going up, because we got to get that water up and out of through the pipe and up and over through the check valve to get into the force main. So even though they might say they're only going to pump this now, but they need to pump the volume what the station's designed for now, not what their flow is now. So that's an important thing to understand. So if you have a pump that plugs up on a regular basis, see how many GPM you're pumping and see what the riser pipe velocity is and your check valve velocity, because that thing needs to open up the whole way to flush all that crap through. Because if it doesn't open up the whole way, it's got to plug. How'd we get here already? So how many people have dry well, wet well pumps? So people that have dry well, wet well pumps, we talk about mechanical seals, we talk about lubrication of that seal. These are single mechanical seals. This is a frame-mounted pump, single seal, close coupled pump, and we put water in that station, water in that seal to keep that seal cool. Whether it's a mechanical seal, whether it's packing, whatever the case happens to be. In today's world, there are pumps that are out there that are 2 mechanical seals. Standard Motors looks just like a frame-mounted pump. But what happens is we don't have to worry about alignment, we don't have to worry about anything else. That motor slides right into that pump shaft, and we have 2 silicon carbide seals. It's much nicer and much more operator friendly than frame-mounted pumps. So we talk about discharge pipe, we don't want it too big, we don't want it too small. When we talk about too big, what's going to happen? It's going to plug up. It's going to have plenty of capacity, but solid's going to settle out, and we're going to have eventually higher friction losses because crap's settling out. We don't want it too small because then we just get water hammer, we get pipe wearing out, we get all those other issues that we have to deal with. So in a station, we look at 2 feet per second in the force main as our minimum design standard when the pump's running. 5 feet per second is typical maximum. Like I said, we have some engineers like to go to 9. That's ridiculous, but they like to do it. And, we would suggest they not. And if we look at 2 feet, 9 feet, so at 6-inch pipe, we'll do 450. A 10-inch pipe, we'll do up to 1,200 gallons a minute. A lot of times we get in situations where we have, especially for developments that are expanding, communities that are expanding, we have a guy that wants to build a subdivision half a mile out of town. Put a pump station out there and bring it back. Okay. So, but he only wants to put in a pump station that's going to do whatever pipe he wants to do. Because he's going to probably be responsible for that pipe. Or the city might. If it's the city, they're going to say, well, there's a lot of land that's going to be sold between you and the city. Therefore, what's going to happen is we're going to take you, we're going to pay to increase that pipe from an 8 to a 10-inch pipe, which is going to help you as a client because you have a lower head on that pump. But what's also going to happen is it's going to help everybody else along the way who's going to contribute and pay back to you as a developer, if he's paying for that station in the force main, to participate in that force main coming back, which is a really good thing. VFDs are a great scenario. We love VFDs for the right application. Sometimes VFDs don't make any sense. They're just a sophisticated soft start. It just depends. You gotta look at the system, you gotta look at the design profile, what you have, but anything greater than 20 horsepower is gonna either have a soft start on it or a VFD on it from that perspective. But you can control the exact amount of flow you want based on that system curve and RPM of that pump. So we'll talk a little bit about electricity. How many people do control panel stuff for their stations? Yeah? Nope. Single phase pumps, usually grinder pumps. Small non-clog pump stations are single phase, are available single phase, depending on what you have power available. Don't do any single phase pumps over 5 horsepower. They don't make very often. If they do make them, it'll be 9 months before you get the pump. So you can convert that voltage from single phase to 3 phase and do a regular size motor for that. All what you can do 3 phase, 230, there's less 208 available today. But 230, 480 is a typical what we usually have. And anything 20 horsepower and up, we suggest soft starts. Your power company may have influence on that. Because your power company says, what happens when you slam a motor, when you turn a full voltage motor on, the bigger it is. It's going to suck every amperage in that line out of it. Just like a kid at McDonald's milkshake. The bigger kid, he's going to suck that thing even drier faster. Same thing. Therefore, what happens is there was northern Missouri, there was a 50 horsepower, 230 volt 3-phase motor, of which they had it across the line start. Wasn't our decision. So they put it online, of which they had a line coming down feeding about a half a dozen homes on this one street. Every time that pump station turned on, every house down that street, you see the power go, all the lights would dim. Every time. This is say, after a few years, somebody complained, said, all right, we're going to change it. So they brought a separate line in, they did some other things because refrigerators start burning up, air conditioners in the summer, all that other kind of stuff. We're challenging. Floats, however you guys do stations and however you do that, your more critical stations, have your station to be much more sophisticated and communicate back to you either on your cell phone, across the line, whatever radio system, cellular system. There's plenty of options out there in today's marketplace. Couple things that are unique. What's wrong with the station on the left? This is what it was before we fixed it. This is what it was after we fixed it. for people that do electrical work on the left is not good. The reason why it's not good is you got some exposed fuses on the door that are 230 volt, single phase. This thing looks like your fishing reel, not very good wiring. Make sure that you can fix it. Okay, make sure you understand it. You have all your stuff exposed, your start capacitors, run capacitors, all that type of stuff. Make sure you can maintain it. What's wrong with this control panel? This one has all your power leads coming from the circuit breaker down to the starter, right in front of all your control relays. If you want to go do if you have a problem with the station, what's going to happen is you're going to have to stick your hand in between all these high voltage wires. Probably not a very safe thing to do. This is soft starts. Reading wire diagrams. A nice station where you have a generator inside a fence is always nice. This is a single phase to three phase. That box on the right is a thing called a rotaphase. So we can take three single phase and generate a third leg, or what we call a manufactured leg, to run a higher horsepower pump. Because all higher horsepower pumps are three phase. So generator is always important from an O&M perspective. Make sure you keep your records. Get yourself an amp probe if you don't have one. Get yourself a voltmeter if you don't have one. Usually those are the same product. You can check ohms. You can do all this stuff yourself and have much higher reliability in your stations so that you can maintain them and they last forever. Southern Missouri high head applications. They called me up one day and said, hey, your station ain't running. Pump's running, but you're not getting any flow out of it. So remember I was talking about wear rings in the past? Well, what it was, they were out there digging up the force main thinking that the force main was plugged somewhere. Well, they go out there 500 feet, dig up the force main, man, water's flowing out of there like it has no end. They go 1,000 feet, flowing out of there like it's no end. Like, what the hell's going on? So they called me up and said, hey, what's the deal? I asked them one simple question. That question was, what's the pressure at the pump? We don't know. Well, if you would have told me that, you would have saved yourself digging up all the force main. So they go back there and said, well, hey, your pressure is 80 feet, or 37 PSI. All right? Your wear rings are shot. Pump's 15 years old. What do you mean, how do you know? Because when you shut the valve and you deadhead your pump, I know that pump is going to go all the way to the left side of the curve, 0 GPM TDH. Therefore, what's going to happen is it's only 37. It should have been 85. It should have been 80 feet. It should have been 95 feet. Therefore, what's happening inside that pump, you're recycling water back past the wear rings, back to the suction side of the pump, and not getting out to the outside. They put new wear rings in. Pump stations still running today. So little pump station wear ring and maintenance is always a big issue to be concerned with. But understand your electrical controls, keep your records, do all that type of stuff, but hopefully now you have an understanding better of what GPM, TDH, and how it impacts between system and pump curves. That's all I got. Questions? Comments? All right, we're going to take 5. We're going to queue up the next one, and we'll go through that. Thank you. Yeah, put a little scotch in that, though. It makes it better, though, you know?
Okay, we're gonna go ahead and finish up today's meeting.
All right, this is the home stretch, man. Now, this is the best topic ever. Pump stations are fun, but this is really good. So how many people operate plants? What kind of plants do you operate? O-ditch?
Oh, we got ditches and aeration bays, and aerated digesters.
Okay. Anybody else? Plants? Yeah, no, kind of, sort of, maybe? No? No? All right. So we're going to talk about aeration stuff. We represent a company called Jaeger Aeration. Jaeger Aeration invented the 9-inch disc diffuser 60 years ago. So when we invented that, how many people are familiar with a thing called a ceramic diffuser? So how many people had a fish tank when they were a kid? Yeah? So how many people had a pet rock in that fish tank? That fish tank essentially was a ceramic diffuser. You blew air on the bottom, and it developed little bubbles on the coming up. Same basic thing that we have in ceramic diffusers. But what do you have to do to that fish tank? What do you have to do to the fish tank rock? You have to pull it out, clean it, throw in some chlorine, throw some lime away around it to get the scale off. Same thing that happened there. There are people got where they didn't want to do that any longer. So they came over and said, we want to have a membrane, a rubber product, to change out our diffusers. So we designed that. Then we designed tubes, and then we now have a thing called the strip diffuser. When we design plants, we want to understand a lot of things about a plant. We want to understand the average day flows today. We want to understand the max week, max month, and max design flows. We want to understand the diurnal curves. What's a diurnal curve? That's the flow that comes into your plant throughout the day. So, for example, we know that at 8 a.m. in the morning or 10 a.m. in the morning, you'll have a higher flow than you do at 2 a.m. in the morning or 4 a.m. in the morning. That's the diurnal curve. We understand that. We want to then be able to calculate how many pounds of oxygen per day based on your organic load coming in, your BOD, your TKN levels, and then we also want to talk about what the effluent water quality is. When we started this business, some decades ago, what happened was people only wanted to worry about BOD and ammonia. Well, today we have to also worry about nitrates, phosphorus, all of those issues. So when we do this, we talk about aeration stuff. Let's see if this is going to work or not. I don't know. There are disc aerators in the business. There's brush rotors. That didn't work very well. There are aspirated aerators, there's diffused aeration systems, and then there are egg beaters or vertical turbine aerators. All of those things generate oxygen. They put oxygen into the water. That is a nitrification process. So what's the difference between a diffused aeration system and mechanical aeration system? Both generate oxygen, but what's the difference? It comes down to energy. So mechanical aeration systems will generate about 3 pounds an hour per motor shaft horsepower. So say, for example, our calculations say that you need 900 pounds a day of oxygen. That's going to give you, a mechanical aeration is going to tell you you need 300 horsepower or per hour. So you need 900 pounds an hour, you need 300 horsepower per hour to do that, 300 horsepower to do that. But you could say diffused aeration system, because the bubble is smaller, more bubbles, smaller bubbles, more surface area that has the ability for that bug to get at that air, at that oxygen. Therefore, the transfer efficiency per horsepower is higher. We can generate 5 pounds an hour or more, depending on flex rate. So for that same 900 pounds, instead of 3 pounds, we're going to reduce that horsepower by about half, which is really good. So therefore now we're seeing energy reductions. How many people have ever heard someone at the city hall say, hey, we need to reduce our power out there at the wastewater plant? Yeah? Pretty common thing today because power costs have gone up. When power costs go up, people downtown say they bitch a lot more. So in our history, this is a standard project. 9-inch disc diffusers on the bottom of a basin, generating X pounds an hour. For every 1 MGD of flow, you're going to have about 1,000 CFM of air with 9-inch disc diffusers. So imagine, how big is your ditch?
Oh, geez. 750,000 gallons?
So you're just under a 1 MGD plant?
Per ditch, so we're 2.29.
Okay, all right,
That's with two small aeration bays.
okay. So 2.29, you'd have 2,000 or almost 3,000 of these guys if we did fixed grid aeration. Probably not very advantageous. Now, the reason why we went to product development, we started out on the thing on the left. Again, I don't know if this is going to work. No, it didn't. Do I have to wait? Can you tell what's running? No? It didn't do anything? All right. So if you go to the web page, you would see that this guy would generate a chimney. So as we went from the left to the right, what happens is that we get more efficient and higher membrane surface area, active membrane surface area. So one product to the right is worth 9 products to the left, 9-inch discs. So one strip is worth 9 discs. So from that perspective, we're starting to now get a better product, and we're getting 15% more efficiency because the bubbles are smaller on the far right with the strip than they are on the left with the disc. That's what this curve shows. So this curve shows a 9-inch disc, which is the standard in the industry and has been since we invented it 60 years ago, is right there. Versus a strip diffuser, which is up to the top. Therefore, the lower horsepower, lower kilowatts of hour per hour, kilowatt power of hour that we use, the same oxygen requirement that we have in the basin. Therefore, we have lower power costs. But the strip diffuser, because it's so wide, we got to do some engineering things behind it to be able to support it, because we're going to be able to turn the air off in this basin and create zones for aerobic, anoxic, anaerobic. How many people have selector basins in their treatment plant? No? Okay. So when we talk about wastewater treatment plants today, we talk about what's your permit going to be. Because we work all over the United States, we have plants that are just nitrification. We have plants that are total nitrogen. When we have plants that are total nitrogen and total phosphorus. It just depends. So when we talk about nitrification, how many people just have an ammonia permit? You just have an ammonia permit in your permit. All right? Most people in here just have an ammonia permit. The further south we go, or the closer we get to the Mississippi River, you now also have a total phosphorus permit. Why do we have a total phosphorus permit on the Mississippi River? The dead zone. Absolutely right. Because of all the phosphorus and all the nitrogen that's being discharged into the Mississippi River, creating so much, there's hypoxia going down. Now, people would say people in New Orleans are pretty brain dead anyways. However, that's a whole different topic than the water. But there's not enough oxygen down there to support fish life in New Orleans and the Gulf. Right around when the boats leave the Gulf. So what happens is that we're point source controlling our phosphorus and total nitrogen up here and discharge into the Mississippi so we don't create so many issues down south. Now, there are bigger plants down south, St. Louis, Memphis, all the other plants on the Mississippi, but ignore that fact. That's a political issue. So, nitrification, we're going to add, when we design a plant, we want to know what the TKN level is. How many people know what TKN level is coming in the plant? Or what is TKN? Anybody? Total kill-all nitrogen. So it is a combination of ammonia nitrogen, which you probably are able to monitor, and organic nitrogen. Now, you certainly don't know what that is unless you send a sample out to a lab, unless you can do TKN levels in-house, which is like digestion, everything else, lab procedure that most people don't do. Probably 99% of people don't do that lab procedure. They send it out to a lab to do it. Organic nitrogen comes in as we urinate. We discharge ammonia as well as organic nitrogen. Depending on that, how far we are away from the wastewater plant, that organic nitrogen is going to convert to ammonia nitrogen. So when we design a plant, I don't want to necessarily know what ammonia is, but that's what everybody gives me. So I always increase it, knowing that some of the organic nitrogen is not counted into that number, and I never want to be short of air. So what we do is we convert ammonia to organic nitrogen, to nitrates. So about every 1 ppm of ammonia goes to 1 ppm of nitrates. Is that good or bad? That's good because you're nitrifying. It's bad because now we're creating nitrates. And why are nitrates bad? How many people do potable water? So what's the level of nitrates in your potable water that's an EPA standard? 10. Why is it 10? Because of, back in the day, blue baby syndrome, nitrates absorb oxygen inside people. So what happens is there were a lot of babies that were born that didn't have enough oxygen. And they came out blue. Therefore, what happened was they didn't do very well. So they figured out that nitrates in the water, and of which people have wells and other things that have been impacted by fertilizers and whatnot, that have high nitrates in water, they've got to get rid of that nitrate for potable water. Same basic thing here. So we're trying to control the nitrates in our drinking water, control the nitrates in our discharge water, of which in wastewater we've got to go through an anoxic zone, or anoxic time, or what we call denitrification, of which we can take that, we have no oxygen in the water, we're not blowing oxygen in the water, that bug is still there, it's hungry for oxygen. What's going to happen, it's going to go suck off that nitrate oxygen, NO3 oxygen, and be happy. When it does that, it generates what? Nitrogen gas. Nitrogen gas goes out into the air, and we denitrify. So now we can go into a facility and say, all right, we want to go and denitrify this basin. We can give you a total nitrogen discharge of less than 5 without changing any concrete, without having selector basins and all the other things that are going on. And the anaerobic is the same thing. We could have an anaerobic basin up front that has no oxygen at all generated in it, and therefore those bugs kind of get sick. They're not very happy. They puke out phosphorus, of which in the aerobic zone, they suck that phosphorus back up like it's a frickin' McDonald's hamburger. They'll go through it like a 5-year-old. But we got to understand how we're going to do this. We know we're going to need air. We know we're going to need all everything else, of which we could be this guy. How many people want that guy? How many people want to be that guy? Not many. So what kind of aeration do you have in your oxidation ditch?
The mechanical. The
Brush rotors, the fingers, the magic fingers?
can't think of the name. It depends on the fins. It's got the fins and everything.
You got the IMCO.
In the area, but what now?
You got either IMCO or Westech. You got egg beaters?
Yeah, egg
egg beaters,
Yeah, surface aerators.
such as,
It's floating, floating blowers and mixers that shoot.
so you have aeration industries. Stainless steel torpedo tubes.
I think so.
Okay? So, if we could do one thing in this business, what would it be? It would make aeration systems retrievable. So we can go back in and retrofit your equipment and give you better water quality, reduce your power, and give you a total nitrogen discharge with no concrete changes. So we've taken the benefit of the strip diffuser. Remember, the strip diffuser gives us more efficiency, higher performance, all of these benefits. Rather than sticking them on the floor all the time, we designed a system to make them retrievable. Because retrievable systems now, back in the day, before mechanical aeration system was available, everything used to be diffused air, all stuck to the floor. But the problem is that construction costs went up because you had to have 2 or 3 basins, because once you had to get down to the bottom to fix them. Now we bring the efficiency back, which now we can give you redundancy and make it retrievable. So we designed a rack. We designed a rack that we can go in and make these all retrievable above grade without dewatering the basin. We inspect them. We can pick them up just like a submersible pump. Hose them off, clean them up, and put them back down the surface. We can install these wet or dry in basins. The benefit of this is now we can cycle the air on and off and create the aerobic and noxic anaerobic zones in that basin without doing concrete changes.
So they're using this a lot like in EBPR, like enhanced biological phosphorus removal.
Sure. Yeah. We could do that. We use these in SPR facilities. We use these in full flow facilities. It's a deployment of a diffuser, regardless of what the process is. Now, we do process design, and some people want to do clarifiers and everything else. We're happy to do that. And some guys say, well, we want to use this guy for our process because we like him, and we want your diffusers in there. Sure, we have no problem doing that either. But you can come up, raise that rack, put your, hose it all off, whatever you want to do, clean it up, and put it back in service. 2 minutes to the surface, 2 minutes back in service. No props. Of which, the tank on the top left is a 2.5 MGD plant, 1 basin. Of which we have the requirements of that job. We could not bring a crane in on site to do any regular maintenance. All the work had to be able to be done with the equipment that's on the bridge. So we supplied the bridge, contractor built concrete tank, we supplied the bridge and all the mixers and everything else. At which time, any one of those can be retrieved with a simple Thurn hoist. But we separate the aeration horsepower from the mixing horsepower. Mixing is all based on the volume and size and the basin and the dimensions. We're always going to maintain that regardless of what the air is on or off. To be able to do that, we need to be able to, we do a CFD analysis, we do some other engineering stuff to make sure that that water is always going to move. Because our goal is to push this water across that membrane diffuser and keep those bubbles all individual bubbles. We don't want them to accumulate together. By doing that, we do that. And therefore, when we have the aerobic time, we're blowing air into those diffusers. In noxic time, we're not blowing any air, we're still mixing that basin. We're all mixing that basin even in the anaerobic time. But we can go into any tank, dimension, style, whatever, and retrofit it. Oxidation ditches. So in oxidation ditches, you can go back into an oxidation ditch. This is one that the rotors fell in the soup, the very top one. They said, all right, we're going to get a new permit. So they brought in a bunch of engineering firms. to come in and analyze what's going on. Because this is in a floodplain, they said, well, we can't build you a new plant, even though you need a new plant. This one's 50 years old. But we got to go over here for 10 million bucks. This is 10 years ago. We'll go build you a new plant. Well, needless to say, that was not a very desirable thing. But what they said was, let's call Jaeger, have them come down. We went down, designed them, and analyzed what's going on. They had plenty of volume in the tank. We changed that process around for $500,000, gave them now retrievable aeration systems, cyclical aeration, to be able to go aerobic, anoxic, anaerobic in that basin. We're saving them 10 grand a year in power, and we're giving them a total nitrogen discharge of less than 5 with no concrete changes. Did the change in 1 day.
For $500,000 versus $10 million.
$500,000 versus $10 million bucks. Same thing in the bottom. So for people in it, so this is a job that we won Wastewater Digest Plant of the Year award in 2023, of which this plant had mechanical air aspirating aerators in it with the little blower on it, of which they couldn't meet an ammonia permit. They had 210 horsepower of aerators on that, operational. During the summer, from May to September, they violated their ammonia permit very often because temperature got up. There's not as much oxygen in the water. So we went in, retrofitted that, put our diffusers and blowers in, again in less than a week. It was like 3 days we were offline, at which time we now give them a total nitrogen discharge of less than 10. We save them $80,000 a year in power, and we now have redundancy that they never had before, and lower O&M costs. Let's see if this is going to run or not. Oh, man. It's a really good video. So, Wastewater Digest, if you YouTube Farmington, Missouri, Wastewater Digest or wastewater, that video will come up. But this basically says they have Larry Lacey, who's the public utility director. They have Brad Bayless, who's the chief wastewater operator, on a video talking about the expansion. And they show some videos and that kind of stuff in it. Great little video. But we also can do this wet. So, for example, if we only have one oxidation ditch in a plant, you can go back in and retrofit that from mechanical aeration to retrievable diffusers without dewatering the ditch. That's pretty cool. We're going to be doing a 15 million gallon per day ditch in Georgia that we won't be able to take offline because they need the capacity of what they have. They need additional aeration capacity because the mechanical aeration doesn't do it for them any longer. But this plant, we went back and gave them a total nitrogen discharge in a few weeks. This plant at the top is Hayes, Kansas. Blowers only run about 7-8 hours a day. Again, we have 28 levels of aeration redundancy out there. We could pick any one of these up and move it away. We do these in concentric rings. We do these in single aeration basins like this with a bridge going all the way across. So we could pick up any of these racks and move it all the way across the basin. The oxidation ditch on the upper right, that's a 15 million gallon per day plant, 2 7.5s. We're going to cancel their expansion. We're going to upgrade all the aeration, cancel their expansion for mixed liquid recycle for anoxic basins and everything else. We're going to save them somewhere north of $350,000 a year in power and cancel about a $50 to $75 million job, simply by changing the aeration process. That's pretty cool. We just did this job at St. Robert. This is a fixed grid job that's down on a floodplain, and I doubt the video's going to run. Hot dog, it is going to run. So that was a fixed grid 9-inch disc job that flooded on a regular basis from the river. And we built a new plant about 50 feet higher.
What'd that cost? New plant?
That was 1 MGD, 1.25 MGD of flow. It was $38 million. 25 of that was all the excavation and dirt work.
Yeah, it looks like it.
But it's a great looking plant. But it took 3 years to build. It was built during COVID and everything else. But you can see we put all the diffusers on the outside. We have the mixers on the bridge. And therefore, we control the DO. We control all that stuff, all the DO and ORP, to control the cycle and understand where we're at in the process. We can also come in and put a bridge with a big X on it. One of these has the mixers on it, one of the aeration on it, and we control the, this is City of Marshall. They're saving about 100 grand a year in power. And getting total nitrogen, total phosphorus less than 5 on total nitrogen and less than 1 on phosphorus. Uh-oh.
It's not going anywhere.
The other marks.
Oh.
So you guys do the diffusers, what about the blowers?
We do everything. We do the blowers, the diffusers, the mixers, the whole package, because it's a process design. It depends how the engineer wants to do it and how the client wants it done. So the ones that you saw bridges on, we supplied every bridge. We got the circle of death. Go and process at the very top. Top left. Very top left. Up, 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 left. Right there.
Oh, well, I was wanting to just kill the one. It's right here.
Changing aeration would beat the heck out of ferric, wouldn't it?
So letting you cycle through them now?
Yeah.
Yeah.
Let's see. So we pick up any rack. If we build a bridge, put it on a brick, put it on a cart, and the video's not going to work. Well, we can push that cart away, and we can retrofit anything. Tank orientation design doesn't make any difference to us. But what does make a difference is we want to select the right blower for the application, whether it's a PD, a screw blower, or a tri-load blower, whatever the case happens to be, to make sure it's the right motor for the right project. And this thing's gonna fizz out on us. I think we're done.
It's locked up again.
Yeah. So we can control DO, we can control the ORP, we can control everything in the process and make it all retrievable without dewatering the ditch. Or make it retrievable for you guys to do whatever's necessary. That from the perspective is really cool. On our website, for people that are interested, we have a brochure. If you want a brochure, we're happy to give you one. Go to the website, learn, just see what we have up there, because it is the process that people are going to end up going to. Because they get the efficiency back. Now they get the efficiency, they get redundancy, they get all the benefits that they wanted before but could never get with mechanical aeration. And by doing that, it makes their life much better. And there's a lot of energy money out there available from the Department of Energy and the feds and through the power companies to be able to help fund some of the stuff. So that's always a good thing too.
How low do they lower? Oh my gosh.
Yeah, oh man, now you're on candy camera.
I don't like this.
How low do you lower the diffusers into the basin?
They go all the way to the bottom.
All the way to the bottom. Okay.
All the way to the bottom. It's just like a submersible pump that goes all the way to the bottom of the wet well. And you can literally pick it up with a third hoist. So we do these, some are on concrete walls, which you can go over and bring a little boom truck over and pick it up, if you can give your boom truck right next to it. Or you can put a hoist on the side, be able to pick it up and rotate it around. Or it'll be a bridge right across the middle of the tank. Depends how it works. Depends what's best for the system. But chances are, for example, like Marshall, Missouri, their blowers only operate about 4 hours a day. Freeburg, Illinois, down near St. Louis, their blowers operate 10 minutes on, 60 minutes off, getting effluent total nitrogen of less than 1, total phosphorus less than 2, all biological. And ammonia is 0. So from that perspective, they're having less power consumption today than they had on their package plant before we built the new platform. Facilities that Farmington, they're saving $80,000 a year in power. They used to use 95,000 kilowatt hours a month. They are less than 40 today a month for 2 MGD plus flow. And they're getting so like I said, they canceled a $10 million job of selector basins and everything else to just do this. They had to do this anyways because the mechanical aeration was failing on them. So they had to do something. So we did this for $500,000 for them last year. But they'll pay for it in about 7 years. So just in power is what they'll pay for. Let alone all the efficiencies and such that they get, lower O&M costs, much more redundancy and whatnot. So there's a lot of benefits to it. If you're interested in learning more about it, we're happy to talk more about it. The video's gonna not work for us, but we can have conversations if people are interested. But we appreciate your time.
I do have one question for you.
Sure.
So on a new construction, like aeration basin, are you guys still putting more disc aeration or are you seeing more strip aeration? And does that depend on volume of the basin itself?
So we would always suggest a strip diffuser. One strip is worth 9 discs. So is it a little bit more expensive? It's about the same, but the disc gives you much more flexibility than the discs do, the strips do than the discs. Most engineering firms, their default is always an 8-inch disc. because they probably don't know about the strips. So until they learn about the strips, we had an engineer the other day who changed his job, the project, away from discs, because that's what they've done for the last 30 years, over to strips, now that they know more about it. They haven't quite got up to the retrievable strips, but they're getting there.
So our treatment plant here, we do an average of 25 mil a day. Our top flow that I've seen since 2013 is 161 mil coming into this plant. So we have to take ours down quite often, clean the disc, do the strips, allow for a longer period of like a cleaning cycle, or are they basically the same maintenance as a disc?
It's less maintenance because you can have less product. All the discs are going to be anchored to the floor. All the strips you could unscrew, pull the strips out of service, hose down your basin. We see a lot of facilities, especially in Florida, that have a lot of debris coming in. They're going to transfer over from 9-inch discs to retrievable strips simply because they can pick them up, they can drop a little end loader in there, clean out the basin because now it has all that sand and crap in it, in the bottom of it, clean it out in 2 days rather than 4 months. It's a little bit more expensive to do capital on retrievable, but the long-term O&M costs, because when they have contractors come in and do that work, they come in, they price it where they're going to gut everything, they're going to put everything back in new, because they don't want the liability and the responsibility of breaking something or anything else. They're going to say, we're pricing it to say all the PVC pipe is going away. On the retrieval, everything we do is all stainless steel. So you can pick that up, tie it off, get your guys in there, clean it up in a day or two with your little end loaders, skid steers, and be done with it.
Now, what's the life expectancy of a strip? Because a disc is right around 9 to 10 years, right?
So black EPDM discs are about 7 to 10 years. You are correct. A strip diffuser will go somewhere between 12 and 15.
Okay. Anybody else have any questions?
How do you know when the disc is worn?
You'll see a volcano.
Okay, so if it's a fine air, how do you know when the diffuser is wore out and needs replaced? If it's a fine air diffuser, it'll just be bigger rolls of air?
Absolutely. You'll see literally a volcano of stuff. Or you'll see plastic material floating in the basin. So you'll see a plastic disc float in the basin, or you'll see a big volcano of air. So when a air system's designed, we create about a strip diffuser gives us a 1 millimeter diameter bubble. Okay? A disc diffuser gives us about a 2 millimeter to 3 millimeter diameter bubble. So what happens is that looks pretty good when you look at it from the surface. When you have a diffuser fail, I don't care whether it's strip, disc, or anything else, you'll get a big volume of air coming up out of that failure point. At which time that bubble thing is going to look like literally Mount Vesuvius, the volcano. You're going to have lava, you're going to have everything coming up out of that thing. You know that that's failed at that point, right below it.
Have you ever had a broken pipe? You know how it releases all the air when it comes up? That's what he's,
Yes.
it looks the same as a broken pipe, basically.
Yeah. There's some videos on the thing, but
Yeah, I'll look at it. Ours have been in for a while, and every now and then I think I see like a hot spot, like 1 or 2 diffusers, but it never seems when we lower the bay down or whatever, it's like, it looks fine when you take the level down. The bubbles are fine and looking okay, so I didn't know.
You'll see it because what happens is that the head goes down, and you'll be able to generate less pressure to other areas if that's happening.
Okay.
And you might only have a small rip versus a big rip, at which time it's going to start to plug up that membrane. So our focus is always going to be all oxidation issues are all mixing limited to about 80% of capacity. At that point in time, then you have to provide enough air to do what the job is. At which time, mixing is always done better by mixers, not air. So therefore, with the strip diffuser, we can go consolidate stuff better and give you better treatment because it's 15% more oxygen transfer efficient than a disc diffuser with a strip. So now if you guys are transporting, say you're treating 40 million gallons a day, average day flow, I'm gonna make a number up, you probably have 500,000, 400,000 diffusers out here, roughly. You'd have 4,000 to do it. You have 10%, you have 1/10 the number of diffusers to do that job, same job. Therefore, and there's some other design stuff that we have in our things on flexibility of hoses and everything else, the way it's anchored, that's much better than a typical 9-inch disc from that perspective. But to retrievable something, because you probably have 10, 12 trains, fixed grid makes sense because you can take them down, with the exception of, in our business, trying to get labor is hard. And therefore, they don't ever want to go down. And so a lot of insurance companies today are starting to classify the wastewater tank as a confined space. So if you classify that as a confined space, that brings a whole lot of other issues than just people. Then you got to start talking about minimum time at the basin, safety packs, blah, 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 which is a pain in the butt to deal with. If you make them all retrievable, that eliminates that from being a concern in the future. So that in itself, we had one client, one of his operators got stuck with a needle through his boot. Well, that's a whole big different insurance health issue for the next 50 years for that guy. So what are you going to do with that? So insurance may have a good play in converting, especially some facilities, back over to consideration for diffused air, retrievable diffused air systems. So we appreciate your time. Guys, have a great weekend. Thank you very much. And don't forget, what's Sunday?
Mother's Day.
Mother's Day. All right. Don't forget your moms. Thank you, everybody.
Thank you. That concludes our meeting today. Thank you for tuning in.